So I'm struggling trying to figure out what to do with lab stuff because this is a time of year when we're doing a lot of labs. But the owl is open. We can be working on the owl stuff. We'll work on some more notes today. And then what I figured is, so this should be what we're doing on Friday. I'm going to try and reorganize the class so it's a little easier to figure out what things to do, what days and stuff. But this should be what we're looking at on Friday. Monday, I'll just kind of work some problems on the board and stuff. And then I'll send out some contact stuff, but in the afternoons I'll have Google Meet open, and so you can certainly come and ask questions there and that kind of stuff. That same time is kind of for all the kids, so it could be chemistry and AP chemistry and physics. I don't know. We'll figure this out as we're going. But anyway, we finished off yesterday talking about temperature effects on things. So today we'll roll into third law. And third law of thermodynamics, right? First law was energy isn't created or destroyed. Energy equals Q plus W. Second law is entropy, right? Randomness of the universe is always increasing. Every process will either make it increase or stay the same, right? So it might not affect anything. But if it does, see stuff flying behind me on the video there. That's weird. Anyway, second law is entropy. And then third law is that the entropy of a pure crystalline solid is zero if it's at absolute zero, right? So a pure crystalline solid with no imperfections means everything's perfectly organized in a solid fashion. And then the only things a solid normally does is sit there and vibrate a little bit. So if it's at zero, not Celsius, 0 Kelvin, then it's not going to vibrate even, right? So it's pure. So there's no imperfections. That would be random if there are imperfections. It's exactly lined up right, and then it's at absolute zero. So such a thing doesn't exist, but that's what we would define as zero. All right, so how does entropy change when we add heat? Well, entropy is randomness. So if we add heat, that's going to cause the molecules to move faster. If they are moving faster, that is certainly more random than if we are not moving faster, right? So moving slower would be less random and stuff, right? And then in calculations, what we're going to typically look at is delta S. So just like we have delta H, which is kind of heat energy, delta S is going to be randomness energy. When we're thinking about those motions, there are really three types of motions. There's translational, which is like your back and forth motion, right? Physics people recognize that from kinetic energy, right? We're talking about translational kinetic energy. There is also vibrational kinetic energy. Now, vibrational can actually have a couple of different kinds of ways, right? So if you imagine, here, I'm going to make myself bigger for a second. If you imagine a Lewis structure of something, right? So you can have two things that they're just bonded together that can vibrate like this. But if you have three things together, like where my body is one of them and this hand is one and this hand is one, they can also vibrate like this. There's different types of vibrational energy, right? And you imagine the more vibrational energy, or the more energy something has, the more of those things are going to vibrate, which is how when you add energy to things, they break down sometimes because they are vibrating so much, they break those bonds, right? You remember that potential energy graph we had where you minimize potential energy? Well, if you heat things up, they're going to wiggle back and forth on that graph more. And if they come up here, well, maybe then that bond breaks, right? So that kind of matches with what we've talked about with decomposing things and with breaking bonds and all that, right? You add energy, you get it to vibrate more and that kind of thing. And then the other type is rotational. So rotational energy being, like spinning around. So if something has energy, it's going to move back and forth, it's going to vibrate, and it's going to spin around in a circle, right? All of those are going to increase, right? The warmer a system is, the more of each of those the molecule has. As a side note, this is 100% why greenhouse gases are greenhouse gases, right? You look at things that are not greenhouse gases like helium. Helium is just a little nucleus, right? So it can't vibrate, right? It can't vibrate. It can move back and forth, but it can't vibrate. And when it rotates, all its mass is in the middle, right? So that's not going to be a lot of rotational energy. Rotational energy happens when something's spinning, but you kind of need that mass spread out. Imagine the ice skater, right? When the ice skater pulls their arms in, they spin really fast. So if something's mass is all on the inside, it can't have very much vibrational energy. So things like helium are not greenhouse gases. Then you think about the other things. Well, nitrogen. Nitrogen is not a greenhouse gas, but it holds more energy than helium does. Nitrogen is two atoms. So can they move back and forth? Yes. Can they vibrate this way? Yes. Can they rotate? Yes, but they can't vibrate this way. And turns out you can actually hold a lot of energy by vibrating this way. So when you look at all of our greenhouse gases, they are all things that have 3 atoms or more. Carbon dioxide, water, methane are kind of your big known greenhouse. There are other ones, but those are the big 3 that we talk about. And all of those have more atoms, so they can wiggle in different ways, right? So it's kind of crazy that all of climate change really comes down to how molecules are able to vibrate. Doesn't make those molecules evil. It just means they can hold more heat. They can hold more energy because of the ways that they can move, right? So hopefully it's nice when we're looking at things like a topic that might know a little bit about, like climate change, and then when you learn about this stuff, those things should match, right? You just because you're looking at it from a different direction, it should still get you to the same answer, right? Whether we're looking at it from equilibrium or from energy or from types of motion or whatever, right? Okay, delta S, systems and surroundings. We really need to be able to focus on systems and surroundings, kind of like when we were doing delta H. Was heat flowing into the system or was heat flowing out of the system? So with delta S, again, that's kind of heat flow because that's going to be how things are moving. If you are exothermic, right? If you're exothermic, then heat is flowing out of the system, and you're going to cause the molecules outside of your system to have more heat and move more, right? So they are more random now. An endothermic process are going to cool off the surroundings, and those surroundings are then going to have less motions and be less disordered, right? So heat can actually dictate the delta S of the surroundings. It's not delta H of the surroundings. It's not the delta H of the system. Of the system, you're talking about the delta S, right? The randomness of the system. But the delta S of the surroundings is dictated by the heat, the delta H of the system, right? So when an ice cube melts, you have now made it less random. But to do that, heat had to flow in from the surroundings. So now the surroundings are less, moving less, and their delta H would be less then, right? So if we look at that in a mathematical sense, you can see that right here, right? You've got your delta S of your surroundings is the negative, right? Opposite direction of the delta H of the heat, right? The change in enthalpy of the heat divided by temperature. So as temperature goes up, it divides the delta H by a larger number, and that becomes less important, right? So if we look at a system like this, you're going from a molecule and an element to a different element and a different molecule. But if we look at this, it's a very endothermic process, right? So if it's so we've got the surroundings are going to get less disordered, right? This is endothermic, so heat is going to flow into the system. If heat flows into the system, the surroundings are going to move less. That means they are more ordered, right? The faster stuff's moving, the more chaotic it is. So as heat flows into the system, that makes the surroundings less disordered, right? The system is going to get more disordered, right? So if the system gets more disordered, that's favoring the reaction happening, but the surroundings getting less disordered favors the reaction not happening. So it's only going to happen at high temperatures, right? I'm in the way here. So that's only going to happen at high temperatures, which makes sense. It's an endothermic thing. So that, again, that should match with what we already know. Endothermic things happen easier at higher temperatures, right? You have to have energy flow into the system, so you have to be at a higher temperature so that energy can flow into the system. So we can predict whether or not things are going to happen at high temperature or low temperature based on whether or not the endothermic exothermic stuff and based on the disorder order stuff, right? We can then figure out when those things are going to be spontaneous. And those two ideas together are called Gibbs free energy. Probably not named after Joe Gibbs, but I don't know who they are named after. So we'll pretend it's named after Joe Gibbs, who was a Washington Redskins coach, right? So those can be used to predict whether or not it is favorable or spontaneous for a reaction to happen. A negative delta G will be spontaneous. A positive delta G will be spontaneous in the reverse direction, and a zero delta G is at equilibrium, right? So this is a thing we just need to know, right? That's a memorized kind of thing. That is, negative delta H is exothermic, positive delta H is endothermic, zero delta H is isothermic. It's the same kind of thing as delta H, just it's also incorporating randomness, right? And this will be both the heat and the randomness together, and that gives us whether or not the reaction is favored or not, right? The spontaneity of it. And that is for another day. So we will work some practice problems together on Monday. Then we will do the rest of the chapter on Tuesday. And then I'll see if I can maybe find some online labs or something like that for this or other stuff. But start working on the OWL stuff if you haven't already. And we'll figure this out.